Hello everyone, this is our first podcast and our second event. We hope you enjoyed Brenda Rubinstein's tutorial on small molecule storage and computation. Please do send us your questions and thoughts as we will be speaking with her this Saturday. Today we are very lucky to be speaking to Rebecca Schulman for the first of our Meet the Molecular Programmer series. Also with me today are the rest of the committee: Anastasia.
Hello.
Boya.
Hello.
Georgios.
Hello.
And I'm Will. Rebecca is currently an assistant professor at Johns Hopkins University, with appointments in both the chemical and biomolecular engineering and computer science departments. She has an impressive past too, obtaining bachelor's degrees in maths and computer science at MIT, and her PhD at CalTech under Erik Winfree. Before her appointment at Johns Hopkins, she was a Miller Fellow at UC Berkeley. She has received numerous commendations, such as the Turing Scholar Award, a DARPA Director's Fellowship, Best at Conference Awards at both the FNANO and DNAX, and not to mention the prestigious Presidential Early Career Award for Scientists and Engineers. And her work has spanned such simple topics as the origin of life and intelligent DNA nanotechnology. Rebecca, hi.
Hi. Thanks for having me.
Thanks for joining us. I thought maybe we'd start with quite a ways back, but a quick recap from your early work and research, just to kind of make sure everyone's on the same page. So how exactly are clays, DNA tile assembly, and the origin of life all connected?
Oh my goodness, that's a great question because it doesn't seem obvious at all. So I guess I will say the genesis of this connection, I should give credit to Erik Winfree, although I think it's an interesting one. So clay, when I started my PhD, for sure was for making pots, but in the field of the origin of life, there was so Graham Cairns-Smith was a chemist who had a very unconventional theory about how self-replicating chemistries that could store information might evolve. And in some sense, many people might say that that kind of chemistry, where you can both store and replicate and then evolve information, would be a kind of, that would be a milestone on the origin of life. And Cairns-Smith's hypothesis had to do with the way some clays are structured, which is that clays can be layered, i.e. composed of sort of different strata, where you might think of the strata as having sort of discrete bands, but also what are called polytypic. So polytypic meaning there's sort of one of multiple ions or small molecule groups that might be present in each of those. And the idea was that if you could make such a layered structure where the choice of this ion was propagated as the layer grow, you could sort of imagine a two-dimensional structure where information is propagated, essentially you could imagine it like a layer cake, where the sort of frosting in each layer, it's a discrete system, is sort of if you read them top to bottom, would be some kind of code, and that the growth of that crystal would propagate that code, and then as clays were in, for example, rivers or sort of some fluid environment, they would erode, which would mean that they would fracture. And then you would end up with, for example, if clays are growing at the edges, if you cut that in half, now there's two sets of edges for that structure to grow. So Graham Cairns-Smith postulated and spent much of his life looking for, but never found, conclusively, although he came up with some interesting micrographs, but he wrote extremely eloquently about this idea. And I think it remains popular in the sense that we certainly don't have any conclusive idea of how self-replicating chemistries arose on the Earth, and potentially in the sense that it involves ubiquitous materials, plausible chemical mechanisms, and plausible physical mechanisms for creating chemical cycles, remains sort of plausible, and there are a set of chemists who think about this idea. So Erik Winfree had the idea that we could connect this notion of clays, or at least say something about this mode of propagation using DNA computing, and in particular algorithmic self-assembly. So the idea that you can actually propagate a choice of, in our case, a DNA molecule inside in our case, a 2D crystal, and that we could represent bands by some stacking sequence of DNA structures that, in our case, we would make a sort of ribbon, and there'd be some stack of DNA molecules that choice of where you could have a choice of one of several in each row, and we could propagate that information as a crystal grew. And so I spent a long time in my PhD thinking about and trying to demonstrate exactly this mechanism. One can debate whether its relation to clays, but I think the notion that information can be replicated in this way, I think it was really exciting to get to use DNA self-assembly and molecular programming to think about in a nice way. So what I showed during my PhD is that we could essentially create a nucleus that programmed some sequence of DNA tiles that should grow by programming the sticky ends off of a scaffolded DNA origami, and then assemble a lattice that would propagate the stacking sequence of information that was encoded in the DNA origami. And then we had these long ribbon structures, and then I worked with Bernie Yerke to design a scheme to actually fracture these DNA structures using what are called extensional flows. So the idea being that if you take a fluid and force it through a narrow inlet at high speed, there's a gradient of velocity around the inlet. So fluid, because water is incompressible, moves faster through a narrow inlet than the larger outlet. Essentially, you apply a force to these crystals, and so essentially you sort of pull on the front and don't pull on the back, so you can snap them in half. And actually people use this effect to, for example, shear genomic DNA for next generation sequencing, so it's a common idea. But anyway, we built a device to apply just the right amount of this extensional flow to break our crystals, and then showed that they could, once they were broken, actually continue to propagate the same information. So we could grow, replicate, because by breaking them we created more ends, and then grow faster in a second generation. So it sort of suggested, by using DNA programming, that this was a viable chemical mechanism, of course in no way prebiotically relevant, but that chemistry did support exactly this mode of information propagation. So that was a fun idea to think about, and maybe a way of using molecular programming that is a little bit unconventional.
So in terms of the prebiotic side of things that you just discussed, have you thought about doing similar molecular programming with maybe like RNA, just like an RNA world hypothesis?
So I guess when I did this work, we didn't have a good sense of all the ways. So I think since I've done this work, maybe one could say, we've learned so many more ways in which one can make regular lattices or assemblies or other kinds of structures using molecules. And it's possible to create these kinds of structures where information might be propagated much more simply. So one could imagine, for example, trying to make aggregates of plain RNA. I guess I feel like one could certainly go down the route of trying to make such an assembly simpler and simpler, and eventually try to demonstrate it with something approaching prebiotic RNA. I guess as I finished my PhD, and maybe I felt like I wanted to try problems in a different direction. I think the problem of the origin of life is a beautiful one. I guess one of the things I thought a lot about during my PhD is that I felt like I think we're very, very far away from having a sense of how life, like where the genesis of the life that we have on Earth. And that one of the challenges was that we don't understand nearly what we should about how complexity can emerge in chemistry in any form, regardless of whether it has direct relevance to the origin of life. And I felt like that type of problem was one that interested me a lot. So how do we understand how chemical systems can propagate information and replicate that information, and what are the themes and ideas and principles and sort of design trade-offs that we should understand in a general sense? And so I took my research in that direction. But I think it it would be a viable and interesting research problem to ask that question. I should also say there are several scientists who have thought a little bit about this problem in the context of inorganic crystals. So Bart Carr, who has been at the University of Washington for many years, has made sort of, I think, salt crystals of some sort, if I recall correctly, where he's been trying to look at similar themes where the patterns of information are propagated as cracks or defect patterns. So that's another way to think about information. So I think there's certainly some interesting questions to be asked in that space. I think one of the challenges is how we think about, how do we, I feel like, I guess my sense is that to directly trace anything to the origin of life, we're going to have to think carefully about how to understand how complexity emerges in these kinds of systems in a much more general way.
So how did all of that lead on to the current work that you're doing?
That's a good question. I think the work evolves. So one of the things, so I guess I can sort of tell you, I feel like where I went from there, part of what I chose to do next had to do with what I said, that I felt like DNA nanostructures and DNA assembly and molecular programming in general seemed like a really fertile place to understand the propagation of information and understanding of the emergence of new phenomena because of multiple interacting components in some defined way in general, and then to hope that it has a sort of relevance in terms of our understanding of how chemistry can create new kinds of forms. And so I think that idea has continued to intrigue me. I guess where I went after that work, I think, had to do with also some of the real difficulties that I identified in trying to make the structures that I assembled. So algorithmic self-assembly is incredibly beautiful. And the sense that you can encode information as essentially a pattern structure of molecules and propagate that information going forward. But I guess if you were to imagine, I guess it has a terrible Achilles heel, which is that how information is propagated is strictly local. So essentially you use whatever the structure of a crystal's facet is to decide to go forward, and all the incarnations that I had seen. And what that meant is, despite, we had spent in the Winfree lab a long time trying to think about ways to make that propagation incredibly precise. So, for example, in your computer, if a single logic gate goes wrong, that could cause, cascading effects. You're going to get the wrong problem to your, addition. We don't do any, but the chances of that happening are absurdly low. I think the last time I heard it was 10 to the minus 23rd. But the best we could do in the lab, I think after I spent a very, very long time and only in certain cases, was say 10 to the minus 4th, which I think in terms of, so if I were to build a crystal composed of 10,000 units, which if I were to make a 3D crystal is not very large, the size of the range over which I could propagate information is disturbingly small. And I guess I wanted to think about ways I could build materials where information was propagated in other kinds of ways. So how do we have longer range communication? And to me, that seemed like an interesting theme that had not been well explored. So in particular, I also really, but I still loved, I guess, the idea. One of the things that drew me to the project I worked on as a PhD is I was fascinated with this notion of evolution, and in particular the capacity of Darwinian evolution to learn or search through space on its own, and the capacity for molecules to execute those algorithms, I think, was a compelling sort of entry in the field for me, as it was for many people, but drawing on, for example, the original demonstrations of Len Edelman on using sort of generating random assemblies and sorting them as a means of doing DNA computing in the 1990s. So I guess so I tried to think for a while about ways to think about kinds of search problems that still involve structure but involve less local interactions. And so what I worked on after that and during my postdoc and also as I started my lab was this idea of I guess what I called point-to-point assembly, which is essentially the idea that I want to use growing assemblies to search through continuous space. And in practice, what it is sort of akin to the problem of bridge building by ants. So essentially, if ants see a chasm, they want to build a bridge across it. So ants will sort of lay down in the chasm and actually form a sort of chain. And eventually, they're going to grow that chain toward the other side to form a bridge. And actually, in practice, they might grow from both sides and sort of connect in the middle. And I wanted to know whether molecules could do something similar. So if I gave them two physical points in space, could I actually instruct some molecular monomers to actually construct bridges? And to me, this was a sort of problem that involved non-local interactions, and the sense that the way we envision doing this is having two structures grow from these 2 points as two linear structures. So essentially, instead of a chain of ants, we're going to have a tube of DNA. That grows via the attachment of small particles at its ends, so DNA tiles. And the idea is that these structures could actually diffuse, and so their ends, if they found one another, could connect to form a chain. And so I spent the next period of time working on that problem. I guess I was also sort of generally interested in the concept of things like graphs, or how do neurons form networks, and sort of this big question of, so this was like the simplest incarnation of that very general problem of how you might build, to me, that I could investigate with experiments. And so we've, since that time, I think, thought a little bit more about that theme that has gotten a little bit closer to some of those ideas. But I was very fascinated by the idea that somehow there's an algorithm for building very complicated networks of components, and that this was sort of the simplest thing. If I were to form a graph, this is a way to form a directed series of edges between them. And so that was, I guess, a very different kind of problem, but it was exciting for me because I think just investigating I chose it based on things that I felt like were just not quite right about what I was studying. And I think that's an interesting theme to go forward. Like, how do we reapproach this problem and that kind of problem is very different, of course. The search that we're doing is in no way similar to the search in evolutionary space of sort of sequences of stacking patterns. But I think I still actually find that really enjoyable.
So for most of these things, you're using square tile nanotubes as the building blocks, essentially, right?
So in that work, we definitely use square tile nanotubes. I think my lab has started thinking about, I guess they're rectangular, but yes, a rectangular lattice. So it's got a much simpler structure than, for example, the really elegant crisscross architecture. I guess, I think one of the other things that I liked about working with those structures also, in terms of just trying to think about research, is I also liked the idea. I wanted to pick this, I think DNA is a wonderful tool, but I guess in the sense that I was building physical structures, I wanted to pick a structure that was very simple, in the sense, if I could get away with it, then that would mean that this was sort of a chemical theme that would transcend, the particulars of DNA being a great tool to sort of precisely control affinity and kinetics and other types of things that people use throughout, I should say, areas like soft matter physics for exactly this purpose. I guess what I liked about the tubes is that they were sufficiently simple. I can tell you sort of physically what properties I would need, and in fact have thought about now how we could implement similar ideas with very different chemistry, some with different kinds of DNA, but also with, for example, proteins or even small molecules type structure. So anyway, I think the idea was that we wanted to pick, I think, the simplest system that would solve the problem. I guess having worked with rectangular structures, I can, for example, certain things were in some ways hard, although I think we have an interesting ways to solve them now. But for example, controlling nucleation is much easier if you have an architecture that has a high coordination number versus a rectangular structure in many cases. But it can be done. And I guess the other point that we learned is actually precisely controlling nucleation wasn't you don't need to be perfect at it. You just, for what we were doing, what we were actually good enough. And I kind of like learning those things, that essentially that it's hard to, every molecule is so badly behaved that I really like thinking about problems where you have to sort of control a parameter, but it doesn't have to be totally perfect, because it's just so hard to get molecules to in any way behave super reliably enough that you would be able to say this this kind of emergent phenomena never happens, because molecules are just very messy.
So is the local error rates you mentioned earlier the biggest challenge you're seeing right now, or are there other challenges maybe constrained to square tiles or just more broadly in terms of implementing the experiments you want to do?
So the nanotubes that we grow don't actually propagate information, in the sense that there's really only one thing they can do. Their length is essentially their information coordinate. You could worry about defects. So, for example, do you make a good lattice? But remarkably, what we discovered is that actually the lattice that we could grow without being that careful was really beautifully good. And one of the interesting things that we saw was that if you grew this tube, so you could grow this strange creature, which is a crystal with no edge. So you could think of, for example, if you have a cylindrical tube-shaped crystal and you formed a circle as the toroid, you would have no edge. And so that's kind of a weird object, so we grew something similar by essentially putting on two origami caps that essentially attach to both ends of a facet. And when you do that, what we found is that you could essentially heat up the system and that those crystals wouldn't melt. And the reason they melted was that they had no edge. But crystals that didn't have a structure on both ends don't melt. And that is actually wouldn't work. It would actually fail pretty catastrophically if there were frequent defects. But we don't see that. And we've learned more and more that we don't have to be careful at all about defects. It seems to not be part of the problem. So I guess we're not really propagating information inside the assembly so much as using the assembly structure and sort of diffusive motion to do a search through physical space. And in that sense, I guess the error rate might be missing your target, but there too, we were surprised to see how difficult that was to do, actually, which is interesting.
So what kind of other difficulties have you experienced? So, for example, in grad school, what were the main, what are some fun memories and what are some challenges that really made it difficult?
Yeah, that's a great question. I think it would probably be more fun than hearing me tell you too much about my random scientific thoughts. So I think the PhD is probably one of the most challenging parts of one's life. I don't think in a bad way. I think I have some very fond memories of doing science as a PhD student. I mean, it wouldn't surprise most people, I think, to hear that some of my happiest memories in terms of the science are really getting to the point where I finally knew how to do the kinds of experiments that I wanted to do. I knew how to design the forms of inquiry that I wanted. And I went in every day, and I didn't have meetings, I didn't have other obstacles, I didn't have to plan budgets or whatever it is that professors do. That is not as fun. And I just got to wake up every morning and essentially have planned my experiment the night before, and I went in and I just did that, and I was just running through, I had to do 30 more of this experiment to get enough, or I knew the sort of sequence of experiments. And it was really great. I really, I'm not a fantastic experimentalist necessarily. I feel like that's not what drove me to do science in terms of being a bench scientist, but it's fun to be really deep into this sense of inquiry and also to have this very prescribed sense that this is sort of your goal and that you've committed to that question and this class of ideas and that you come in every day to do that. And I really enjoyed that sense of then, for example, first, I can tell you, I think the first thing I ever figured out that was worth writing a paper about, the first, time I really came up with my own model to explain data and had to convince my professor that this was actually a good model. And he was like, oh, he's like, I wouldn't have thought that would work. But then once you explained, he believed it. And that's really exciting. And then, I think the idea of being able to giving my thesis talk is, of course, really, I found that really exciting. My tenure talk, so I'm actually an associate professor and not an assistant, but thank you for making me feel younger. My tenure talk actually had some technical difficulties, and it was there was some projector software update that didn't work, so everyone was angry and waiting for 20 minutes. So that was terrible. But my PhD thesis was really fun. I really just loved, it was a nice story. I loved sharing it, and I was really proud. And I will say, as a faculty member, it's still some of the best days of my job to see my students graduate, because it's just, I think it's kind of like a wedding. It's like ritualized. It's very exciting. It's a big transformation in your life, and everyone's happy. And I guess, but, from the science point of view, it's like I watch my students, I'm like, wow, I wish I had given that talk. That is awesome. And, I just love that transformation. So for me, also that sense of pride and accomplishment after having worked so hard, I think was certainly important. So the less good things, I guess, I think there are different classes of things. I mean, a PhD is though there's this wonderful part where you find the right problem and you're chugging along and you're, and maybe there's several problems, depending on how you structure your PhD. But there's also the times when you're clear, you're not only lost, you're lost, and you're not making progress. You're either working on a project that doesn't work and you're not sure how to solve it, and something's going wrong and you don't have any sense of how to get out of that space, or worse, that you feel like there's just something bigger wrong with the way you're approaching this problem, or the kind of science or the kind of question you're even asking is just incremental and not the right thing, or not useful for the bigger problem you want to solve. That can be very draining. And I feel like I felt maybe a little of all those things at different times in my PhD. I had technical problems that delayed my work by several months. But I think the lowest parts were certainly the ones where I really didn't know what I should do for my thesis, and I hadn't done much of anything in the first few years of my PhD, and I felt like this sense of maybe I was just really, I don't want to say failing at this, but just not going anywhere. And I think that was very difficult. So I think it's very hard to figure out. I guess the problem with a PhD is that ending up with a good PhD means a chance for all students sort of ending up in that weird place where you haven't gone the right direction. And so there's risk, if you've taken a risk, then maybe you ended up there. Or maybe, your advisor gave you a terrible problem. I don't know. But I certainly feel like that's a very difficult part. And I mean, there are the other difficult parts, which is, learning to write your first paper and all the drudgery and the long times it takes to do work. My advisor was very, very sort of, had very, very strong opinions about how he wanted things to be in my paper, and I'm not always the most detail-oriented person by nature, so I think I made 45 versions of one of my figures for one of my first papers, which I can't say I enjoyed. The figures came out well, and it was probably, I think I hope I don't get to 45 versions with my students, but I understand what he was doing in retrospect. But those are, I think at the time those are hard. They're hard things to do, and they take a tremendous amount of energy that I think is hard to comprehend. Like as a faculty member sometimes, and hard to remember how difficult they were for people. But I guess, and everybody finds certain aspects of the PhD, different aspects of the PhD difficult, I think. So that's also kind of hard to generalize, but those are maybe some array of my own thoughts.
Yeah, I think those will resonate with a lot of our listeners. It certainly resonates a lot with me, some of those challenges. Do you have any advice for people going through the same difficulties?
Yeah. Well, I guess I forgot to add one thing, which is I think one of the hardest parts of a PhD is it's like the worst thing, but I think maybe it's a good thing, given how hard it really is that you can't quit, right? So after about your third, I guess in the US, the PhD for us would be about 5 years, maybe in Europe a little less, but sort of about halfway through the typical PhD length, you're so far from finishing, but you can't quit because it's like the worst, terrible idea. And, and there may be various reasons to quit. Like maybe you're frustrated, you feel like you're not doing anything, maybe you're, the people you work with are horrible, or maybe you just hate this field. Like there are many reasons why you might be stimulated to feel that way, but you can't. And so feeling like that feeling of trappedness, I think, is maybe one of the worst overall things. And I want to say maybe to those of you out there who feel this, it's structurally built in, and I think it probably should be addressed, but I don't have any specifics. But I think that's one of the most challenging things. So maybe in terms of advice, I feel like you're not alone on that one. And so but so I guess maybe the lesson I learned from that is I feel like if I have a student who I'm not really sure is really like willing to just like do anything, like is just so passionate to get through, I'm very clear to them right up. I'm like, this is the best moment. If you're not thrilled your first year with everything that's going on, find a different direction, because there's gonna be this point where you've got no return. And if you don't have that like love of doing this thing that's almost irrational, or the drive or something that's gonna really push you through, you're not doing this. If you have any ambiguity, right, going in, pick a better, not saying don't do a PhD, but I'm saying find that thing that you just cannot imagine not doing, because otherwise it's brutal. So I think that's a big one. I guess maybe my advice might also come from having mentored PhD students now. And also, I felt like as I mentor more PhD students, my thoughts on how getting through, having a good PhD experience and really growing and meeting your goals as a PhD student have evolved. And I think in terms of what is going to help you out, everyone knows, being really smart doesn't hurt, but there are these other things that I think make a huge difference in how people do. One of the most important lessons that I think can't be stressed enough, and I, as a computer scientist, are entirely antisocial, and I love nothing more than sitting in front of my desk and reading, doing analysis, writing code, and seeing what happens when it works, and like thinking and not talking to anyone for a long period of time. That said, I guess I can see a very strong correlation between people who are really good at reaching out to others, to ask questions, to work together, to seek out their expertise, and to work communally, and success certainly in what I do, but and so I constantly, and also asking for help. So saying, for example, like, this is not working, I'm not really sure what to do, and sort of prompting not only your own advisor, but your colleagues to help you solve that problem, and also getting feedback. So how could I be better? And then more importantly, listening to that feedback, which is brutal, right? I mean, I'm guessing most of you have gotten back a paper and the reviewer's like, this is not interesting, or, said something mean or wrong. And, so we're filled, and every professor's, I think, that I've ever heard of has had grant proposals rejected, and we've all been rejected from jobs and schools that we wanted to go to. It's hard, and it's constant in academia. I guess learning from the feedback that you get in a way that's productive is really important. So how do you take the review, there's this phrase that, for example, the reviewer is always right. The reviewer doesn't, so for example, if they say your work is garbage, that's not right, but the point is they're coming honestly. I'd say 90% of reviewers are honest. And so, taking feedback from people and being honest with yourself, but also not beating yourself up over it, in the sense that we're all struggling to improve at any given time, is really important for getting through. And learning to live with criticism and failure is emotionally is very difficult, but it's incredibly, and it's important. It's not something I started out being good at, and I'm probably still not good at, but it's really critical for survival. I think maybe one of my pieces of advice is to not take things personally, that almost nothing in science is personal. It's not about you. It's just about the experiment not working. It's about, things could be, we're all working and improving. And I feel like that can be a hard lesson. I know I've seen students that when, you say, well, why don't you try it this way? Because their design of their experiment or their inquiry was, I felt like I had suggestion. If you take that personally as a criticism that you're bad or weren't doing a good job before, it's going to make this process very difficult. I'm not saying you should start that way, but learning that for me, has been certainly helpful. And it's helpful to go through everything that you go through in terms of applying for jobs and sending in your papers, is trying to look at feedback as a learning experience. And that's the ideal, right? We're down here, but trying to keep perspective about that. I guess, yeah, so I think those are big things. I definitely would say read lots of papers. That joke about an hour in the library saving a month in the lab is not actually a joke. So it's, but of course the challenge is knowing what papers to read. How do you find the right papers? How do you read them carefully? It's a really important, and how do you learn from your colleagues, right? So more generally, do you go to talks so I think that's really important. But I've noticed that when students really prioritize that, and also when they get into a new, try a new kind of experiment, they go read 5 papers about it and learn about what different people have done carefully. Or, when you take on a new technique, really take the time to understand what related work is like in the field is challenging, and it's not as much fun, honestly, as trying stuff out on your own. But it's really important for making progress and also contributing to science as a whole. And I will say I've noticed a big correlation between students who make that a priority and people and being successful going forward. And really also that gives you the opportunity to find really cool solutions to your problems if you get good at solving, because you can read an unrelated paper and learn get an idea from it as well.
So on the topic of spending a month in the lab, what was it like going from somewhat like a kind of a theoretical background, computer science and mathematics, and moving into doing bench work? What was that transition like? Did you have someone mentor you, or were you kind of left alone and someone said, figure it out?
I feel like I was probably somewhere in between. So that's it's been a while. So I studied computer science and math. I should probably back up and say that I probably came in with some background in experiments. So my mother is a biologist, and I definitely got this idea that I was sort of interested in molecular science in college. So I did this very silly thing, which is instead of taking some kind of computer science lab to satisfy my lab requirement, I spent the second term of my senior year doing biology lab with a bunch of pre-med. So I learned how to pipette and I guess I also worked as a high school student at the National Institutes of Health, where I actually did a lot of RT-PCR to do analysis of RNA in rats. So I had some background, although certainly the particulars of my experiments were all new. I don't think I had a formal mentor who was specifically interested in my project, but there were definitely more senior people around who were helpful, who would kind of show me some things about what to do. I'm trying to remember, probably Paul Rodemund, who started as a postdoc at the time that Erik Winfree started his lab, was probably taught me a number of techniques, as well as Erik himself, having done so. I think, but in terms of things like pipetting, I think I figured out a lot on my, like in experimental design, I figured out a lot on my own, although I don't think that's necessarily wise. So one of the things I try to do in my lab is really pair senior new students with a particular mentor for the first 6 months, whatever kind of project they're doing. I feel like you need somebody you can go to that you feel like is charged with answering your questions and has the time to do so, to help you go forward and feel some responsibility for doing that. So I think that's important. I think there are many ways to run a lab. I remember once I had a seminar speaker who runs a very large lab, and I asked the speaker how he managed such a big lab, because I felt like I had to see all my students, and he told me, he said, he's like, for the first 2 years, he said, I don't talk to my students at all. It's like they don't. So there's sort of in that lab, there's some self-organized form where students learn from each other. There's not, and it works out. He's very successful. So I feel like, I think it's important to say there aren't good models, but I guess, the right model. There's sort of, if it's working for you and for students are happy and you're productive, it's probably a good model for you. I think, but I guess it took me a long time to understand how to organize and plan experiments. I think this also is, I feel like the project management side of experimental science, and to some extent computational science, depending on what you do, is underappreciated, in the sense that, you can, I guess I learned by the end of my PhD to the night before plan all of my experiments and like what, maybe even for the week, plan what I was doing and really have a sense of where I was going, kind of like a but also fit in different things. I didn't have like a full schedule, but I kind of understood what could be done in one day and was very purposeful and organized about it. And then also on a longer time scale, I knew I need to do this series of experiments to get something done. And I think that kind of skill I definitely didn't have. I mean, I learned that for me. Probably other people do things differently, but I definitely have found in talking with students that if I'm explicit and give advice about that, not just like here's the experiment you should do, but also how you might plan and do experiments, that's really, for some students, it's really important because that notion hadn't occurred to them. So I actually feel like that, even though learning specific new techniques is always talked about, that aspect of training to me, I think in terms of planning your time is really key, especially as you move from being a beginning grad student when you have all the time in the world to like later in your career when you suddenly realize you have to get things done before, and all that you want to you have all these things you want to do, so you have to figure out how to get them done.
So conversely, I guess, do you have any tips for those people who maybe actually do come from like very experimental backgrounds and might be trying to break into the theoretical side of things? I mean, for example, like, or maybe to those people who are kind of stuck in the middle, like myself as an engineer, I'm kind of somewhat confident in the lab, but I'm not exactly able to go and on the theoretical side of things, I can't exactly go down and prove a theorem just so as easily as kind of the more purely theoretical people can.
Yeah, no, I think that's a great question. I guess I didn't really answer sort of how I learned to be an experimentalist, so I could maybe go back and think about that. I think for both of these things, I guess there's practice, and I think definitely having somebody to like not only work with but get regular feedback, and also be willing to ask the question which is going to get you the constructive criticism, for example, so that if you're not doing something right. So I feel like those are all key things to learning a new skill. And also maybe not underrated is asking the really, that's actually really important, is asking the stupid question. So the thing that you're sure everybody in the room knows but you, and that you're actually, for example, so, you're like, what's a lemma, right? If you were learning to prove theorems, and I'm sure you probably know that, but I'm saying if you didn't, there's no point in not, you can go look it up, right? So you should, Wikipedia and internet and the scholarly resources are your friend. But if it's not clear what something is or why somebody's doing something, I feel like it's a really, really important part of learning a new skill is to identify what you don't know how to do and ask. And it's not really necessarily for example, and also asking people, for example, how they got somewhere. So how did you get that step from, what made you think, and just how did you write this proof? Because they will present, when you go see a proof, they'll present it, but it's it's created in some nonlinear fashion. It might be created straight backwards, right? That's a really, that's a great, it's actually a classic mathematical technique to do so, right? That, so I think those kinds of operational questions, how do you do something, where did you go for somebody, I feel like most people are willing to answer because they're really interested in their own work. So you ask about somebody else and you think about it. So how do you do something like somebody else? I guess the other part that I think one of the most valuable pieces of advice I've ever been given to learn to something new, which is whenever you start any kind of scientific inquiry, no matter what your technique will be, is sort of knowing what the form that you want the answer to be in, right? So if you, for example, want to understand, why do fish swim, right? So what kind of answer are you looking for, right? Do you want, for example, an experiment that if I pull off a fin, this fish doesn't swim anymore? Do I want a fluid mechanical theorem, like the scallop principle? Do I want a computer simulation? And so one can take that idea and actually break it down even more, which is, why do I, so example, if I want to learn how to prove theorems, I feel like if you're not going to, that probably won't happen. But if you say, I really want to understand sort of the answer to this kind of question, and this is the kind of answer I want, then I feel like you can work back and think about what are the pieces I need to start to address that. What tools am I missing? And really ask very specifically about these techniques. I guess if you really want to learn how to prove theorems, there's a couple classic books, I guess, about logic. One is called like How to Prove It, that I read, I think, in college. It's very good. But which is just a very constructive thing. I think the other thing as an engineer I learned is that there are sort of methods that you can use. There are heuristics for almost anything. So, they probably won't get you there, but if you don't know about these heuristics, it's probably, setting you back. So, and these are true for her experiments. They're true for, all kinds of experiments, for, for whatever kind of inquiry we're doing. And I really like understanding process. So I think those are, I think you can see that from my answer.
But like, why do you think, why do we see so many people who are essentially, or people coming from a theoretical background, theorists, moving into disciplines which lend themselves very well to experimentation? For instance, for example, in synthetic biology, many labs at their head have people who started out as theorists in, say, pure physics or maths and have ended up starting purely experimental labs, which are then guided by, like, why does the net flow seem to be in that direction, and why do we not see people moving in the direction?
I think the answer might be purely operational, which is the ratio of students to jobs, and there's just many more theorists, there's not a lot of theory jobs, and so then all the people, those jobs are probably mostly, you're going to be most competitive if you have the most experience, perhaps. I mean, you could answer that operationally, maybe that. I mean, the other, I guess I can say for myself, I mean, having started as a math major and thought about it, I guess a couple things drove me from it in terms of making it a career. And I guess one of them was also that there are only so many jobs as math professors, so you really have to be really excellent at it to get that job. But maybe the other thing was also, I think there were a couple other things, but one of which is, I went to I actually spent a little while as the PhD student at MIT, and I remember thinking in CS theory, they were like, okay, well, here's matrix multiplication, and so, we're trying to shave these exponents off, we have a order 2 to the 0.006, and we want to get down to 2 to the 0.003, and I probably don't even have the orders right here, but the point was, it was a sort of small, there are these big problems in theory that take 30 years, right, or 100 years, or 300 years, depending on the kind of problem. And this idea that you're going to work on this very, very technical piece of a piece. It's not that it's not worthwhile, it's just it didn't necessarily appeal to me at that time. I guess in terms of molecular programming, though, I guess for me, what drove me from theory, from theory at the time that I worked to doing more experiments is this idea, because I should say that I really started out doing much more theory than I ended up doing even as a PhD student, is that it's very difficult in chemical sciences to make a really good theory that you can stretch that much without having some experimental sense. So, for example, we can make theories about algorithmic self-assembly, but if the problem is that we don't have the model right, and that, for example, I think one of the problems I found is that this sort of assumption of perfect cooperativity of interactions between multiple bonds, for example, is just not physically correct, then you could spend years on this crazy trajectory that's not, it's going to take you places that end up having a limited value in reality. Because it's not pure math, right? In the end of the day, when we think about molecular programming, our goal is that it's relevant to molecules. So if your conception of your molecule is not quite right, then you're in trouble. And so it seemed to me that you really either needed the experimentalist to work with you, or to have that data out in the field that's going to keep you calibrated, or in my case I felt like there wasn't anyone doing that, so I said, well, gee, I gotta go in the lab myself, because otherwise there's not going to be the data I need. And I think it might be the case that for many people who go from theory to practice, there was some aspect of that they really got curious about something, they understood they needed data from experiments, but none of the experimentalists wanted to solve that same problem, so they're like, well, I have to go do it myself. In the sense of doing experiments, I think I have seen some students go the other direction a little bit. I I don't know that I can answer for the world at large about why that isn't a problem, but I don't think it's the case that there's some fundamental difficulty going up that hill per se that just can't be done and that experiments are easier, because I feel like they're very different. But and some experiments are very easy. Honestly, some computer programs, you're going to like press the same button a lot of times and switch some parameters. And so it's not that it's easy, but it's also not necessarily deep in the sense that it requires like a PhD level understanding of abstract mathematics at all times. So I don't know. And I guess I would say, though, now with, for example, machine learning, maybe, for example, or, I feel like people are actually going back in the lab. Like if you do see a little bit of this migration the other direction where people see this opportunity to go do this new kind of analysis, and that you have experimentalists, and I've seen them go back and start doing much more, maybe not theoretical, but much more computational work. So I think that we'll see how that goes going forward.
So as you hinted at, in addition to the sort of theory versus experiment divide, like our field, molecular programming, is super interdisciplinary. Like, for example, for your experiments, presumably you need a decent enough understanding of computer science, but also maybe how like DNA works and maybe the biochemistry involved. So in sometimes it feels like somebody to succeed needs to be like a jack of all trades and understand a lot of things and be able to put that together. Can you speak at all to that from your experience?
Yeah, I think that's a good point. I think Ned Seaman has a good joke about that, about how you have to be a bravura chemist, physicist, molecular biologist, artist, like mathematician and computer scientist. And I think you can look at it that way, but I think maybe to me, I think fields like molecular programming really point out the power of having that, not looking at the world strictly from a traditional physical, like sort of department or discipline-centered perspective. But I guess maybe to point out that we all only have 24 hours in a day, and it's not that molecular programmers get to do 3 college degrees. It's just that you have to, or 3 times more coursework. I don't think that's right. We have to figure out how to learn what we need to learn and how to use that. So I guess that also sort of comes into this sense, like I told you, what are the things that make students successful? What I found are people who ask people for help and people who read a lot in in journals and books. I feel like that might speak to that idea, that the sense of what our background needs to be will evolve. You don't need to know everything. So I definitely don't know a lot of things in chemistry or chemical engineering where I work, but I know DNA and RNA chemistry pretty, much more deeply than any other type of chemistry. I know the kinds of chemistry that apply. Like, I don't know much about solid state chemistry or physics, for example, because I didn't learn them. But as I needed to learn things, I went and go and found them. And I feel like that's what I see you guys do, that, as you learn things, as you need to know things, you go figure out how to learn them. And that that you can go from very different kinds of backgrounds to appreciating, different ways of thinking. And I think that's kind of how we have to work, but I also feel like that's an incredible strength for students. So I tell students, whether or not you stay in academic research, that this ability to figure out this constantly evolving landscape of, not just what I need to know now, some new tool, CRISPR, it's like didn't exist 10 years ago, right? So we had, maybe not quite 10, but you get my point. But then, so you have to learn about it and become an expert in this new area, but also that, maybe I need to understand, for example, a little bit about we need to know what different things like about protein chemistry or, some new analytical technique. Like I need to actually know some physical chemistry to understand how it is that NMR works, because that's, but I feel like just sort of thinking about how to learn those things to us is a strength. I guess the other part is, of course, putting all those things together into a coherent way to ask, how do I shape my work? And I think my point about knowing the form of the answer you want is super helpful. Like I feel like I focus tremendously on what is the problem I'm trying to solve and what am I looking for, and really then focusing so that then I can identify what I need to solve those problems. So whether it be an expert, something I don't know. So I think we're always going to be learning. I think the question is figuring out how to use what you know and how to fill in those gaps when you need them is something that I think is a strength. I think it's really exciting that you guys have formed this organization, because as I said, I think talking to one another is probably the most important thing that one can do. Because I guess one of the things I've tried to do in my lab is have people with very different kinds of expertise. So, I have a physicist, I have a surface chemist, I have process people who really love process engineering. I have somebody who loves to do complex simulations. I have a couple of biologists. And I feel like that kind of interaction, biophysicists, like these people who come at the problem from very different ways and can converse, that's a really exciting thing about our field. And so it's not that you need to know everything, but you need to know how to talk to people who know all these things to figure out how to get the problems solved. And then, as I said, how to learn your part and how to fill in gaps so that you can understand what's going on.
Those are very encouraging. So I wonder if a student only have one side of the background, and he may feel that the stuff he does not know is a lot, and he may develop imposter syndrome, like feels like, oh, he does not belong to this field, and there's so much stuff that he does not know. I wonder if you have ever experienced imposter syndrome, or if you have any advice on that.
Yeah, no, that's a great question. I think that term has pervaded society for us, hopefully, to feel like I've definitely experienced imposter syndrome, and it comes in big, flashing signs, like I don't belong in science, I'm gonna quit, to like these micro things like, oh, they're talking about this thing I don't know about, so I'll just let everyone else decide, when you kind of understand there's something not quite right going on, right? So it comes in all these forms, and they're all different. I think the key is to just trust yourself a little bit, and to I guess also recognize that idea, right? That there's always this sort of self-doubt a little bit, and but I think I guess, I'm not sure if I have deep advice about this, but I guess, as I said, one thing I feel like maybe helped me that you wouldn't expect is actually the answer, asking dumb questions. And when I say dumb questions, I really mean they probably were dumb, and it's not like people are like, oh, that was actually a really good question. I don't care. Maybe there were questions I asked because I wasn't paying close enough attention to what somebody was saying. But I feel like it's that almost generally, if you were polite about how you ask a question, people are very happy, but like, oh, like you use those pipettes? Like, I remember as a grad student, like I did not know how to use or as a postdoc, I did not know how to use two-part epoxy. And I spent 6 hours trying to glue something together. So two-part epoxy essentially comes in two parallel toothpaste tubes, and you squeeze them out together, and the two components react to form a plastic that's a solid, and the two components that are reacting are a liquid, so the way you dispense it. Anyway, I had this idea that you applied them in series, and I was very carefully pressing one of the tubes all around all the this very complicated glass things I was trying to make for my biophysics experiment, and I was so frustrated. And then I would apply the other one, and this just didn't work right because the tubes are designed to create this kind of mixing. I was trying to make the simple sort of fluid cell, and I spent hours and hours and hours, and I finally asked. And it was a really dumb question, because honestly what I was doing was really silly, and I could have looked up on the internet how to use two-part epoxy and figured this out on my own. I also have not been able, for example, find the microscope power switch, and those things add up, but I think the key is to that. I guess I'm telling you these things also to point out that you can survive even if you have these, and maybe your silly things that you really feel embarrassed about. You're a great experimentalist, but maybe there was something else that struck you. We all have these moments where it's we just feel like everyone else knows, and you're just really confused. But I think, and I remember spending all this time working up the nerve to ask. And I really feel like once I did, it was so much easier. And I feel like I don't even care if people think silly because I've asked 60 of those questions. At the end, you know what? I asked those stupid questions about, how to screw this thing in, and how to make a shim out of aluminum foil because, I'm just totally, just don't know because I'm a dumb mathematician. But, at the end of the day, I did some darn good science. And the reality is then I also feel great when people ask me the silly question. So I want to maybe say that there's really things that we're embarrassed that all of us don't know and that it's okay to ask. I also want to say that in some ways, molecular programming, I think, is a good place because it's not like theoretical physics where there's this sort of like clear sense of the specific things that you need to know in this precise body of knowledge that you need to have. And it's really sort of almost clear how to get at these questions. And so you either kind of know or you don't. For us, there are so many ways to ask the same question that it's actually really that almost everyone is, if you're disciplined and thoughtful and really clear on what the good questions are, you have something to contribute to those questions. So you can come from many, many different backgrounds, and so I think that's an exciting thing. So find people that you like and trust to work with that have different skills than you. Don't be afraid to ask when things are difficult, or as I said, if they're the silliest thing, things will be hard that you didn't expect, and you'll have those days. But and I don't want to sound Pollyanna-ish about it because, as I said, imposter syndrome doesn't go away. It just keeps going. I still feel like I'm like, what am I doing here? Like, why did they ask me to do this? Because I have no idea. But I think the key is to say try something. You don't have to say something, but try something and see how it goes. And that you have to remember that all the time. But I think the other part is in molecular programming, there's definitely not a right answer. There's so many ways to think about things that the question is really more, how do I, figure out how do I contribute? Because everyone has something really exciting to contribute.
Kind of a shifting gears, what do you think you might do if you weren't an academic? Are there any things you do in your free time that you might turn into a full-time career?
So, I actually worked in Silicon Valley for a few years before I went to grad school, and I thought about being a programmer, and I liked writing search engines. But, that's kind of a boring answer, honestly. And I also decided I didn't want to be a programmer because I felt like it was like hard to do. I couldn't imagine doing it until I was like 65. It just seemed too draining. So actually, I really like to cook. So that was another thing that helped me learn to do experiments. And actually, my mother's family is Italian, and almost all of them before. My mom is a scientist, but almost everyone worked in the restaurant industry and also making wine. And I don't know if I want to make my living doing that either. But if I wasn't an academic, I'd probably be cooking a lot more cool stuff than I am now, at least that you could eat. I hopefully cook some good stuff in my lab, that in a different way.
And what would you tell your younger self back in 2000 or maybe when you were just finishing your PhD in 2007, if you could go back in time?
Yeah, I really don't know. There are definitely things I would have done differently, but I feel like it's just hard to, of course I know the answer to lots of problems that I wondered about for several years, or that, maybe I'd tell them about, about all, whatever, I'd tell them about Sherlock, right? If I knew about that in 2000, it'd be good, right? So for example, like some new DNA, some new technology that we didn't have. But maybe more seriously, I feel like I don't ask that question. I think because I get asked what I'm going to tell, not my younger self, but younger students every day, right? That's kind of my job. And so I feel like I got a lot of great advice myself that I'm really grateful for. And I feel like having learned more, as I said, like what is going to help you as a grad student, maybe I'd tell myself those things. But as I said, luckily, and I'm not saying everyone has this, I think largely I had good advisors and good advice, and that I feel like that was great. And in fact, in some ways, I feel like the advice other people tell me is much better than the advice I would ever tell myself, because they have a different perspective.
Do you have any regrets in graduate school?
I'm not sure I like I feel like regrets are terrible things to have because you can't get rid of them, right? They can't be fixed. I certainly could say there are probably things I would have done differently. And I definitely don't want to say like things went perfectly and there would have been no way to know how to do anything else. But I guess I just don't think about regrets in that way. I think there were maybe, directions that I might have chosen. Like, I think, maybe I would have thought about trying to, I think I probably would have read more papers and thought about, like, really been less afraid to expand my thinking a little bit and trust myself. Like, we do a lot of chemistry in my lab now, and I feel like I think about how difficult it was for me to start thinking about. And I think I would have probably tried to learn things a little bit out of my comfort zone a little more. But at the same time, I think I did. I learned a bunch of sort of interesting systems biology and control theory, and like spent a while reading like interesting papers. And it's not the same knowledge that I use now, but it created a great foundation. So I'm not sure that it's fair to have asked myself to shove in even more things that I learned either. But that said, I think if you have, it's fine to have regrets. I don't know that I conceive of having specific things. I've definitely done my share of stupid specific things, but I don't know that they're really that exciting for anybody else to think about. Oh, I did tell you about the two-part epoxy. I wish I had actually gone and looked on the internet about how to use that before like spending a day crying about it.
And looking to the future, just switching gears again a little bit, where do you see our field going? Do you see any maybe like killer applications for molecular programming, DNA nanotechnology? And are those applications something that drive you, or more of just the beauty of molecular programming?
I think, so I guess I was shocked when I started my job, because I think what got me into molecular programming is I just found it intrinsically curious. So I guess it's not that what drives me is total curiosity, but I feel like some students really come and they say, look, I really want to cure cancer, right? And I don't, they don't care about how they're going to do it, right? They're like, tell me like, what is the right way? That's what gets them up in the morning. And I'm definitely like I like to think about molecules and think about molecules doing interesting things. But I do feel like you could study anything, and so many problems will be interesting. So I'd like to choose one that is not only interesting for me, but also really has implications beyond that. And I also increasingly feel like that's my job. Both to, raise research funding, I need to make that case, but also as a scientist entrusted with federal money and entrusted with, educating students, I feel like that's also an important part, that science is curiosity driven. But as I said, given the choice of 100 great problems, I should pick the ones that are of being equally great, that also have real, some kind of impact going forward. That said, my lab does a lot of very basic, design of and sort of asking about things that don't have any immediate application, but with the idea that if we could solve those, that they would have their uses. In terms of what I think are interesting, I think there are things that I think are really interesting and exciting for the field, not all of which I necessarily feel like are the things I'm the right person to do. I think the, idea of using molecules for, DNA storage, I'm not sure DNA is necessarily the right ultimate tool, but this idea of using heteropolymers to store information in mass and think about computing is cool. I'm still not sure where it's gotten a killer app, and so maybe it will not make it, but I feel like it's an interesting idea. I guess in terms of molecular programming, one of the things I think is potentially really deep and transcendent is this idea of really embedding molecules and logic into matter to instrument it. So I guess maybe the best example of that is something like DNA macroscopy, where you're actually going to use like molecules and molecular operations to actually measure distance and think about the shape of something. And I think I actually think that's kind of a simple example, like in terms of how we embed molecules into materials, how we embed them into cells to instrument, for example, recorders of data of, what a cell is doing in terms of like, transcribing or, making DNA molecules that you then read out. So, I think there are very many ways to think about that problem, but I really feel like that idea, people always ask, I'm sure you've all been asked, are you going to use molecules to solve ordinary differential equations? No, that's silly, right? I don't think that's right. Molecules are interesting for programming because they are part of matter and materials. I think those are the problems that excite me and I think are really interesting going forward. I mean, I think it's still it's useful to think about pushing the bounds of how much computing we can do in different ways, but I feel like in the end, in terms of driving how molecular programming will change our experience and where it will sort of fit into the body of science as a whole, I think that is a place that I am really excited about. And I guess maybe there are many ways to think about that, sensors. So I guess those are all sort of, how do you use computation to do things like sensing? They all sort of, I think, integrating a lot of that together will be really powerful. And I think could change the way that we think about materials and certainly about biology and probably chemistry and going forward.
I think that's a really exciting outlook for the field. And with that, probably about time to wrap up. Thank you so much for joining us, Rebecca. This was an amazing start to our podcast series. We hope you had a good time. We certainly did. And we'll be back in a few days with Brenda Rubenstein to follow up on her fantastic tutorial on the small molecule technology her lab uses for storage and computation. Thanks so much for listening. So goodbye from me. And goodbye from everyone else.
Goodbye.
Bye.
Goodbye.
And see you shortly.